Okay, so let's keep going. Let's talk about Gibbs free energy. So the Gibbs free energy is a new state function. So we know we know H, right? And endothermic or exothermic, we know entropy is increase or decrease in randomness of the universe. And we put these two energy things together to give us the free energy or the Gibbs free energy. So this is the most important equation. We're going to use this a bunch and we're going to look at it in a bunch of different ways. Why do we care about the Gibbs free energy? Well, at a constant pressure, temperature and pressure, the delta G tells us if a reaction or process is spontaneous or not. That's why it's important, because we can figure out if something is spontaneous or not. If we're trying to create a new reaction, or we want to, do some new thermochemical reaction, we can find out how spontaneous it is just by doing a little bit of math, just by actually just looking up values. Okay, so the breakdown of this is there are three values this can be. Delta G can be negative, delta G can be positive, and delta G can be equal to 0. Okay, so if delta G is negative, and you have to know this stuff, it is going to be a spontaneous process. So when you calculate a delta G, and we're going to be calculating them, if it is in fact negative, it is spontaneous. If it is positive, it is non-spontaneous. And here's the tie-in from the previous chapter. If it is equal to 0, we are at equilibrium. Okay, so at equilibrium if delta G is equal to 0. There's a quick little mention here, plus or minus 10 kilojoules. We can assume we're at equilibrium if we're at plus or minus 10 kilojoules. 10 kilojoules is a small amount of energy, so there's always a little bit of buffer just during calculations. So plus or minus 10 kilojoules. So it's not technically 0, although most of the time it's 0. So we say 10 plus or minus is what we're looking at. So understanding the free energy equation. So free energy has two terms. So my delta G is equal to delta H minus T delta S. Again, this is the big equation that we're looking at. So of those two terms, let's just do units quickly. Typically, we're going to report delta H in kilojoules, and delta S is going to be measured in joules, which we typically convert to kilojoules. But actually, sorry, joules per Kelvin and kilojoules per Kelvin, because then we're going to multiply by temperature, which is going to be in Kelvin. So this term right here is my enthalpy. And this whole term minus T delta S is my entropy. Well, kind of the entropy term. Again, the temperature is always in Kelvin because we want that absolute value. We don't want any negatives. And G is reported in kilojoules or joules, but mostly kilojoules. Okay, so that's typically what we're going to look at. All right, good. I don't love this plot, but I know that a lot of people use it. So let's kind of take a look at this. So we're going to take a look at the plot of Gibbs free energy as a function of, so Gibbs free energy, so delta G as a function of reaction progress. So over here, I've got 100% reactants. Over here, I have 100% products. And so this can change depending on the type of reaction that you have. But what you can imagine it looks like is, what it's going to look like is it's going to dip down somewhere and it's going to kind of look like this. So a couple of things. So right off the bat, we can say where it equals 0, where it is at its lowest, might not be there, it might be right here-ish. Where it is at its lowest, okay, that right there is going to be equilibrium. So this is where this is going to be our equilibrium position. That means that on either side, we are going to be in a Q, okay? Because what I do know is it's going to be spontaneous in both of these directions. And if we compare those delta G values, so if I compare this delta G versus where we are, so the difference of these is greater than 0, right? This should be negative, but it is going to be spontaneous in that direction. Again, final minus initial. Final position minus the initial position should give us the initial positions less, so it should be negative anyway. But it is non-spontaneous if I try to go in the other direction. Okay, so at any point, we have equilibrium, and then we have Q's on the other side. So again, we're always going to descend down to equilibrium at some point based on that reaction progress. So that's the concept there. And so ultimately what it comes down to, doing these calculations, we are using our delta G naught is equal to delta H naught minus T delta S. And we have to do those calculations for delta S. And we can actually do these calculations based on the appendix. There are many ways to get delta G. And because delta G is a state function, I don't just have to use this to find delta G. I can also use an equation like this to get delta G as well. In fact, I've got to fix one of these. It looks like this is delta H. So the other way that delta G can be calculated is delta G naught is equal to the summation of moles times G, delta G of products minus the summation of moles times delta G of reactants. So much like the others, I can get delta G this way, or I can solve for these and plug it into this equation to get delta G. So there's a couple of ways that we can actually get the delta G values. All of those appendix ones we can actually look up. So calculate the standard free enthalpy formation of NO from N2 and O2 at 298, given that delta H, all right, so we're already given delta H values and delta S values. So given that these two terms, so delta G naught is equal to delta H naught minus T delta S. And so delta G is equal to what? Well, my delta H is a positive 180.7 kilojoules minus my temperature, which is 298 Kelvin, make sure it's in Kelvin, times delta S, which is 24.7 joules per Kelvin. Kelvin's going to cancel. Right now I'm in joules in one and kilojoules in the other, so I'm going to change this to 0.0. I'm just going to multiply by 1,000 or divide by 1,000, so 0.0247 kilojoules. Multiply it all out, and you get a delta G value of 173.3 kilojoules. Ultimately, I don't really care about sig figs because what I really want to know is delta G is positive, and therefore it is going to be not spontaneous in this direction based on the information that we have. Okay, that's what we're really pulling out of all of this. So with that said, calculate the standard free enthalpy change from the energies of formation. So we're going to do this a little bit differently now. I'm going to look up these delta G values, and you can look these up in the appendix of your book. So we find out that P is 24.4 kilojoules per mole. Cl is 0 kilojoules per mole. Most elements are 269.6 kilojoules per mole as well. And so do that calculation. So delta G is equal to, again, summation of products minus summation of reactants. So you should do the reaction, what you find out, and hopefully when you do this calculation, you find out that delta G naught is equal to negative 1102.8 kilojoules. So what do we know about the reaction? That's right, the reaction is spontaneous. Reaction is spontaneous. So that being said, what is the delta G of the reverse of this reaction? So delta G naught of the reverse of this reaction would be what? That's right, positive 1102.8 kilojoules. So this reaction would be non-spontaneous. Right, spontaneous in one direction, it's non-spontaneous in the other. Okay, so good. So we know how to calculate delta G's. There's two ways to do it. I either do it with the summation, I guess I can finish this, the summation of moles of delta G products minus summation of moles of delta G reactants. Or we can use actual delta H and delta S values. Again, we can calculate these two values the same way that we just did, and we can solve for delta G, okay? So how do we predict the spontaneity based on temperature? And so I want you to be able to create this chart, but temperature is going to have a major effect because I know delta G is equal to delta H minus T delta S. So knowing these two things here, or knowing this equation here, I need a positive or negative value. There's a couple of things that can change. So delta H or versus delta S. So if delta H is negative and delta S is positive, what does that mean? Well, if delta H is positive, delta S is negative, the delta G value is going to have one fixed thing. So if delta H is negative, and I can actually just plug this in. So delta H minus T delta S. What that ultimately means is delta H is negative minus the, remember, temperature is absolute, delta S being positive, right? A negative minus a positive is always going to give me a negative value for delta G. So what this means is, in terms of what the reaction result is, it is going to be spontaneous at all temperatures, okay? What about if we take a look at if delta H is positive and delta S is negative? Well, what does that say? So if delta H is positive minus a negative for delta S, plus minus a negative means plus plus a positive, right? So that means delta G is going to be positive. It is going to be non-spontaneous at all temperatures. Okay, so those are the easy ones. Okay, so those are the easy values that we can actually get there. That's the kind of stuff that we're looking for. So let's take a look at what happens if they're both negative. If both of these values are negative, so let's see, delta H is negative minus T, which is, and then that is negative as well. So the way that I want you to think about this is I want you to look at the extremes. So if I make temperature very, very low, so let's just say that I make this equal to 0, right? So if I look at a very low temperatures, so at low temperature, what does it actually do? So at low temperature, in fact, I'm going to use red again, right? Yeah. At low temperature, okay? So this becomes 0, okay? So a negative minus this whole thing becomes 0. So negative minus a very small value, it is going to be negative, or it's going to be spontaneous. Typically what we're going to see is at low temperatures, we are going to see a negative value for delta G at low temperatures, because this whole term essentially just goes away. The other option is what happens if I have the same setup, but I have a negative minus T negative, but instead this is a very high value. So let's just say that this value is, I don't know, 10,000 degrees or something like that, right? A really large number. Well, generally the delta H is going to be really small in comparison, and this term is going to go away. So what that leaves behind is a negative minus, or a negative, those both become positive, and this becomes positive, it is going to be non-spontaneous at high temperatures. Again, we don't need to know this chart. We just need to be able to think in terms of low and high temperatures. So let's try the last option. What happens if they're both positive? Okay, so if they're both positive, a plus minus a temperature plus. So at low temperatures, so if I turn my temperature to 0, it's blue or something here. If this goes to 0, this whole term goes away and delta G is positive. There it is, non-spontaneous. And then finally, if this is positive minus T, and this is positive as well, but temperature is massive, let's say 10,000 again, this whole term goes away and we end up with a negative value. So it is spontaneous at high temperatures. Okay, so that's the idea. We should be able to predict spontaneity based on those values. We just have to plug those in and kind of see ultimately what happens. So we run into questions like this. So temperature and spontaneity, when the signs are the same, we're going to predict that there's a temperature where things change. Okay, so is there a temperature where the reaction is no longer spontaneous? Again, if one term is negative, one term is positive, or if the terms are opposite, doesn't matter what the temperature is, they're spontaneous or non-spontaneous in all direction. If the terms are the same, temperature is going to matter. Okay, so with that said, let's take this and I'm going to plug in these values and you're going to do these calculations. Oh, sorry. Is there a temperature the reaction is no longer spontaneous or non-spontaneous? Well, we know that in that case where they're both the same, one's going to be positive, one's going to be negative. But what we really know is when delta G is equal to 0, this is the transition between spontaneous and non-spontaneous. So what this question always asks, and this is a favorite question, is what temperature is delta G equal to 0? That's really what I need to figure out, because then I can say, all right, well, this is the temperature we go from where we're at equilibrium, right? Because that's what delta G equals 0 is, right, at equilibrium. And either side of that, we know we're going to be spontaneous or non-spontaneous, but depending on temperature. So we have to calculate delta G. That's what we have to do. So I'm going to write out this chart. Moles, value of S, value of H, S naught, and delta H. I could look these up and do these calculations, and I think it's worth doing. So we know that those 1, 2, and 3, and my values of S are 191.6, and my H values for those elements are going to be 0, 130.7. By the way, this is in, I'll put the units on the last one because there's the most space there. 111.3, negative 80.29. And this is going to be moles. This is going to be joules per mole Kelvin. And this is going to be kilojoules per mole. Okay, so let's do the calculations. Calculate the delta S for me, and as well as, so what is delta S? What is delta H? So do those calculations, pause it and do those calculations. Hopefully for delta S, you got negative 361.1 joule per mole Kelvin, and you got negative 160.6 joule per, or kilojoule per mole. Okay, actually not even mole. The mole shouldn't be there because they're going to cancel out. So joule per Kelvin and kilojoule for that one. Okay, so let's do this calculation then. So delta G is equal to delta H minus T delta S. So delta G is equal to 0. Delta H is equal to negative 160.6 kilojoules minus temperature, because that's what we're solving for. And delta S is going to be negative 0.3611 kilojoules per degree Kelvin. Solving for this, I figure out temperature is equal to, hopefully what you got is 444 Kelvin. Great. And that is the break-even point. And so now the question is, well, if they're both negative, we go back to our little chart. We could do this the other way as well. At both negative, anything lower than that is going to be spontaneous because it's low spontaneous at low temperatures, meaning it is spontaneous below 444 Kelvin. Okay, that's how we do these calculations. So do the same thing here. Look at these values up, and I will actually give you the answer. Temperature should equal 1052 Kelvin or something close to that, if you, depending on the constants you use. But I think I got these from OpenStax, so you should be able to get that. There is a whole thing in your good. Okay, so last little bit. Connecting these things together. So we looked at this Gibbs free energy. We saw that equilibrium is connected. So we are looking at this whole time, we're looking under standard conditions. But we can also look at it under non-standard conditions. So standard conditions is standard temperature pressure. Non-standard is not STP, okay? So delta G, this is the equation for that. Delta G is delta G naught. Again, that's under standard conditions. That naught is telling you standard conditions. RT natural log of Q. So this is under non-standard conditions. I can solve for a non-standard delta G by adding this term to the delta G naught. So this is an important equation to know. Generally, you're given this. I'll have to look and see if you are, but I will always give it to you. Rearrange this equation, you get two things. So delta G naught. So yeah, under standard conditions, all of this goes away. So at equilibrium, Q equals K and delta G equals 0, we get rid of that delta G naught term. So under that, in that situation, delta G is equal to 0 plus RT natural log, and Q becomes K. Okay, so what that means is delta G naught is equal to negative RT natural log K, meaning I can find that delta G based on temperature and based on the equilibrium constant. Or I can kind of do the E of both sides. K is equal to E raised to negative delta G naught, or negative delta G naught, yeah, over RT. Again, there we go, okay? So these are important equations to do. Oh, yeah, this does become naught because we're now under standard conditions again. So delta G drops out, and that's what we ultimately have. Okay, all right. In fact, that's confusing, so I'm just going to get rid of it. But this is the important equation, set of equations here. This is a helpful set of equations here. This is to find to understand. I'm just non-standard conditions. This is to figure out delta G naught based on Kelvin. So based on, sorry, not based on equilibrium constant. So calculate this, figure out this out. Delta G is equal to delta G naught plus RT natural log of Q. You should be able to solve this because you can know what a Q is. Again, Q is nothing more than products over reactants, and you have product and reactant values there, so you should be able to figure it out. Hopefully, when you do this calculation, you end up with negative 44.9 kilojoules per mole. So please do that work and see if that's what you get. Make sure your temperature's in kelvins. All right, good. That's it. That is the equilibrium. This idea connects the idea of equilibrium to thermodynamics, and that's what we're looking to do. And last one is electrochemistry coming up.